It's great to be back here again and to be joined by an extremely interesting panel from around the world. Now, I was struck recently by a McKinsey report that suggested that the automotive industry could be one of the biggest beneficiaries in the long term of quantum computing. That is, in the long term, and we all know this industry is still way out there. But I'm hoping that the four speakers I have with me today are going to shed some light, not just on the big hopes their companies have for this technology, but what they're doing in the nearer term to get some benefits and to prepare. Starting furthest east in Tokyo, Dr. Takanori Ide of AISIN. Dr. Takanori, thank you for joining us before dawn where you are, I think. In Europe, Oliver Wick, who is a technology scout at BMW, Florian Neukart, the director of the data lab at Volkswagen. Hello, both. And closer to home in Michigan, Joydip Ghosh, who is the program lead for quantum computing at Ford. So let's dive straight in and look at the long term. And maybe Joydip, I can start with you on this one. What are the one or two things that you really think quantum computing can do for your business and really make a difference in the longer term?
So in the longer term, we are definitely thinking about all the discrete and combinatorial optimization problems that emerge in the mobility sector as well as in the logistic that we have. Apart from that, a big chunk of our thrust that we can envision is going to be in the material science simulation, material design. And, when we think about just not about the cars, it's about kind of everything in terms of materials that you are going to use in battery and everywhere else, right? The third thing that I can think of is quantum machine learning. The big question, though, in all of these cases is where we can see the right use case with some computational advantage. And many of those things are probably under the current active research.
Oh, thank you. By the way, I should have said we're going to do a lightning introduction to the future of quantum computing in just 20 minutes. So I really appreciate our speakers being very succinct today, Joydip. That's a great start. I'm going to come to you now, Takanori. What do you hope to achieve at AISIN?
Achievable in short time or long time?
In the long term, first of all.
Okay. In long term, we believe that the benefit of quantum computer is to remove heavy computational time appearing in big data calculation, such as logistics and automotive parts design.
Thank you very much. And now I'm going to come to Florian Neukart at Volkswagen. Florian, what are you working on?
So I agree with what has just been said. For us, most interesting in the long term is material science. And here, one use case that's already been mentioned is, of course, battery chemistry. So if you're able to use one quantum system, a quantum computer, to simulate another quantum system, a molecule, exactly, that opens the doors to many things. But battery chemistry is the thing that is most interesting to us. So how can we design better cathodes, anodes? How can we design batteries, increase the charging cycles, increase the durability of these batteries? So that's the long-term goal in that area. And in the short term, please.
No, I was going to say, so really longer term for electric vehicles, this is going to be a key technology.
Yes, it is. So as Joydip just said before, it's interesting for many areas in construction and automotive research, but battery chemistry is the one that I would consider to be most interesting in terms of quantum computing. And in short term, the things that we are working on right now, anything optimization, so that will go on. So any traffic optimization, any logistics optimization, any delivery optimization, anything that really has to do with optimization of fleets, number of vehicles, routing. So that's all interesting.
Yeah. Well, let's dig more into that in a moment. But first of all, I'll come to Oliver Wick at BMW. Oliver, why is BMW investing in this technology long term?
Yes, I have to explain that a little bit in two sides. The first one is we have to invest in the process areas. That means we would like to improve our internal processes for development, for production, for financing. I would like to explain that a little bit. Development, there we have a lot of optimization activities, material science. Florian and Joydip mentioned that in the battery area, but also in software validation and verification. And of course, of machine learning cases where we can accelerate it specific parts of the machine learning process. On the production side, there we have job shop CX scheduling, a lot of different optimization areas, and also for financialing, because we have treasuring, we have to make secure the materials on the world, and there we see some things. And on the product side, normally there is actually no way to transfer a quantum computer into a car, yes, but you have to see that we have some function which are cloud-based, navigation, etc., etc. And there we see an individualization of functions in a car. That could be navigation in this way.
No. So from what you're all saying, I mean, I guess the message coming through here is that across the value chain in automotive, you can see benefits, in all these areas. I guess from where we're sitting now, this is still many years out, at least, quantum supremacy or quantum advantage in the kind of way that we're all anticipating. So shorter term, what do you think might be achieved? What are you working towards in the next, say, 3 to 5 years, both in terms of applications, but also developing your own capabilities and expertise internally? So tell us a bit more just about that, about how you're working towards this. And maybe, Florian, I can start with you. You talked about optimization. I know, Volkswagen, you've worked on some of this already. What kind of results are you seeing, and what do you think you might be able to achieve in the nearer term?
So one thing, or the first thing that we started looking into a couple of years ago in terms of quantum computing was traffic flow optimization. And while that didn't solve all the traffic problems in the past, or the current traffic problems in the world, we're still looking into that. So we have improved it over the years, and any optimization in the mobility sector. So what I mentioned before, optimizing fleets. So how many vehicles do you really need based on traffic? So if you want to optimize taxi fleets, or if you want to optimize public transportation. So is it possible, if you have buses like we did last year in Lisbon, if you have buses and you have static bus stops, is it still possible to route them dynamically between these bus stops? Is there an advantage? So all these problems, they have a time component. And while these problems are still solvable with classical computers, you may just have an advantage with quantum computers by being faster, by being slightly more accurate in shorter time. And that, call it some sort of business supremacy, that can already be an advantage for companies. So if we save minutes or even just seconds, that may not be interesting for a theorist, but for a company, it may be interesting. And in a short term, I mean, optimization is what we will look into. And of course, we try to downscale problems. So when we talk about material science, for example, simulating small things, lithium hydride, beryllium oxide, really, if you can do that already with the current quantum computers and compare it with classical algorithms and see that the result is the same, that may tell you, well, you developed an algorithm that works. And as machines grow, you may be able to do something that's more relevant to industry.
Florian, you said, I notice you use the word may. Is there any way of saying so far from your work whether you will see any of these results? And so when you talk about optimization, for instance, we're all familiar with quantum annealing as a technique for optimizing that's already being experimented with. Are you actually getting results, and are these tangible benefits?
Yes, we do. And here, I must be very careful with how I formulate it. The advantage that we see is really the time that it takes to solution. So if you have a problem that takes a certain time to solve with a classical machine, can I get a better solution at the same time with a quantum machine? So this is what we're looking into, and this is what may be interesting for us. I give you an example, and this is, so it's traffic optimization. So which is a combination, at least when we look at it, how we do it. So it's a combination of a classical algorithm where you have a prediction, predict traffic 15 minutes ahead, 20 minutes ahead, and then you do the optimization. So you redistribute the vehicles that you predict will contribute to traffic jam such that the traffic jam doesn't occur at all. But if this redistribution takes longer than the prediction interval, then it is no good. So therefore, we're looking into ways to solve these faster, and quantum annealing systems are one way to do that. So while you can still solve it classically, you may be faster and achieve an advantage if you do it quantumly today.
Thank you. Takanori, maybe I can come to you now. So what do you think you might be able to achieve within, say, a 5-year time frame? What are the techniques that you're working on right now?
Yeah. In short time, we are focusing on solving critical automotive part design challenges, including quality assurance in automatic transmission software, because automatic transmission is very, very complicated control. In addition, we are researching big data calculation on logistics service. Now, there are different types of quantum computer, such as superconducting, ion trap, and photonics. Therefore, we need to verify the efficiency of different types of quantum computer to solve downside problem.
Right. You talk about the software problem with transmission systems. How are you trying to solve that problem? And when do you think you might have a solution? Is this a near-term challenge for you?
Near term. It's near term. So to assure, it has to explain. So
understood. All right. Well, I appreciate you. Thank you. Yeah. Thank you very much.
Thank you.
Oliver, let's come to you. What is on your plate in the nearer term, and what do you think you might be able to deliver?
Yes, okay, let me explain it a little bit. In former times, we did a lot of proof of concepts, yes, together with a startup like Q2B, yeah? And there we find a lot of issues regarding the maturity of quantum computers, yes, and we have to accelerate or improve our skills in that way. And so we thought, okay, is it a good way that we as BMW will invest in this topic, or should we go to another companies which have the same challenges and in order to find the right level of exchange? And so actually we are looking for in the whole quantum computing stack and way of an integration way. Yes, and it could be that we could find a mathematical model, and this mathematical model could be run on a specific algorithm and on a specific machine. But from this stack here, that is always the same. That is at the guys at Volkswagen, at the guys at Airbus is always the same. And so I am not really interested to run benchmarks inside BMW. The idea is to run benchmarks from Airbus, Volkswagen, etc. in a more or less in an organization, and then to transfer these results into the companies. And so that is actually some activities running in the European Union, in Germany regarding the Corona program, yes, and also in Bavaria. And there were some hubs, and we have to coordinate all these hubs working between research and industry. And this is for me actually a very, very important topic to coordinate all these strengths together.
Excellent. Thank you very much. And finally, Joydip, maybe I can come to you. What are the intermediate technologies and applications that give you hope here?
Yeah, so already other panelists talked about the mobility and other sectors where we know the problem formulations in terms of optimization problems. I just like to add one thing here. In the short term, the way we are defining it, what I can see, the way I can envision, is probably that the news that the quantum computer is coming up down the line, it's actually giving a huge push in some classical approaches, right? So people are trying all sort of quantum Monte Carlo schemes. You can think about quantum inspired technology and things like that. Now, if you add that in the bigger picture of quantum, I think you will be seeing a lot of hybrid computing that can see some business path, right? So when I say essentially this hybrid computing, I mean some quantum approaches working alongside with some classical solver or maybe some classical hardware platform, and also quantum-inspired algorithms implemented on some not von Neumann but other form of classical hardware as well. And if I add this entire picture, then yeah, I mean, not only in the mobility sector or the logistics sector, we can think about huge problems that people will be attempting to solve. For example, the big supply chain optimization problems, or even simulating very complicated molecules.
Thank you. Well, now we've got time for one more very quick lightning round. And I've saved the big question for last, which is, this is obviously a huge investment, a huge uncertain investment over a long period of time, and a very difficult one for companies to make. So when you look ahead, what is the one biggest challenge that you think you're going to face, whether it's technical or in just persuading your organizations to back this idea? Well, what is the thing in your mind that's the toughest, and how are you going to deal with that? Again, if we can just do this very quickly, I'm going to start with Oliver, and we'll go around quickly with that question. Oliver, Rick.
Yeah, sure. The biggest issue is for sure the business case. Yes, we do not have a business case in the short term. And so we need a lot of argumentation about the management. Why is it necessary? And I have here a similar approach. In the last time, you have to argument why we need digitalization. Yes, and nobody understand it in a really big thing. And yes, you have to rebuild your processes for digitalization. And I think it's quite the same matter. Here we have now quantization, yes, and we have to check, is our process able for quantification? And so I think that is for us the biggest challenge. And for sure, we need a lot of good talents. And there we need a quantum physicist and subject matter experts and a digitalization guy in one person or in a team.
Quantization, there's the new word for today. Takanori, what is the biggest challenge you think you're going to face?
Yeah, so I want to explain the biggest challenge of AISIN group. So we would like to develop quantum optimization and quantum machine learning to improve the efficiency of the entire logistics service related to automotive manufacturing. Thank you.
Thank you. And Florian, what is keeping you awake at night?
So we don't have a business challenge. So at Volkswagen, we appreciate quantum computing, and we already decided it's strategically important. I see the challenge more towards education. So there will be a lack of talent very soon. So once machines are available or systems are available that can do things that are industry relevant, we'll not have enough people to hire because everyone will be interested in hiring these people. And the other thing, it's also not a challenge that we have per se, is scaling these systems. So especially when it comes to gate model chips. So I would see this as a challenge for the whole industry. So can we really scale these systems up to millions of qubits, make them fault tolerant? So that's a big question still.
Just a small issue there on the technical side. And Joydip, I'm going to finish with you. what is the thing that you think is going to be the biggest obstacle ahead?
Well, I mean, in the quantum computing community, I'll say that we very closely monitor the development that are happening from the hardware side. So I do know that in recent times we have seen some very concrete vision how you can go to all the way to making a fault-tolerant quantum computer. It's not obvious, but it's good that we are making progress there. But this is something probably some sort of a challenge that we will be talking about many years from today. That's one thing. And another thing is, even in the sector of quantum algorithm development, I want to see some diversifications or the variations, right? So the quantum algorithms that can really give you advantage over the traditional computing has been limited to a few different sectors. We do know how to formulate one type of problem to another type of problems, and then probably we can make a get around with it. But in general, I'm hoping to see more discovery in the area of quantum algorithms.
Got it. Well, thank you very much, Joydip. Thank you, everyone, for joining us today for this very quick trip around automotive. Gentlemen.
Thank you very much.
Thank you.
Thank you.